moving on to webinar 3, the third part of the webinar, is I'd like to describe in a few case studies and show how do you choose your method of crystallization. Often people ask me, what will we choose? How do we do it? So again, coming back to what we started. In the first place, those of you who have just joined in here, I just reiterate some of the things I've said. Main problems for crystallizers are no crystals at all, tiny low quality crystals or phase separation or just precipitate, and large beautiful crystals that either diffract poorly or don't diffract at all. And choosing the crystallization method can have a significant effect on the result. So what I'd like to show here is several practical techniques, again, that can be set up manually, and some using robotics, rational and practical guidelines how to use when, and again, examples of successful crystallization of difficult proteins. So choosing a method depends on your problem. Are you getting showers of small crystals? Is your crystallization going too fast? Are you getting no crystals at all? If you do get crystals, are they stable? So various questions. And the most common method for crystallization, which everybody uses, is the vapor diffusion, which is a dynamic system. There's changes in drop volume, there's changes in pH due to volatile ions. Also, slight temperature change can cause dissolution of crystals, and this can be very frustrating. And concentrations of the ingredients are changing during the crystallization process. So really, you don't know where you are at any stage, really. And to overcome these limitations came the birth of the microbatch method, and we designed that with Douglas instruments together to overcome the problems with vapor diffusion, but also initially the goal of it was for miniaturization and automation, because this is going back to 1990, long before the era of nanotechnology and high throughput. And in those days, also using vapor diffusion, people used 1 microliter drops, so this was too much. And so we came in to try and design something which is completely different. So it was, as I say, the main goal at the time was miniaturization and automation. And for miniaturizing, you had to prevent evaporation of drops. And we also wanted something that one can control the crystallization environment a bit more than all this changing scenario of the vapor diffusion. Now, microbatch is already an established method, but still many people are not aware of it. And even those that are aware, they've got some worries about it and asking various questions that I hope to answer here in this webinar. Detailed things which sort of worry people when using it. So for those of you who are not familiar with microbatch, it is a method where you set up trials under a layer of oil, a low density oil. And the first oil was paraffin oil, which is a density about 0.8 as opposed to a density of 1 of a crystallization drop. And on your right, you see the mechanism of dispensing a drop under oil. You go, you take the dispensing tip. This is done. You can do it both manually and robotic. Now, all robots do microbatch as well as vapor diffusion. The original one was the Impex robot, which was designed here at Imperial with Douglas. And you dispense a drop under the oil, and because the drop is heavier than the oil, it sinks down to the bottom of the well and sits there. Now, many people say, oh, oil, how will we see the crystals under the microscope? So here I'm showing various examples that there's no problem at all. The crystals are just as visible as they are under vapor diffusion or any other method. So the difference between vapor diffusion and microbatch is really the different routes that they take to crystallization. Those of you who have watched the first webinar, I showed that the different methods take different routes to arrive at through the nucleation and growth stages. And vapor diffusion is a dynamic system where the reservoir acts to gradually concentrate the drop, and it is a change in concentration that may lead to crystallization. Microbet, on the other hand, is a more stable method. It's really the simplest method. And in the old days, people crystallized with batch, but of course with quantities of liters. The batch, the crystallization are dispensed in microbatch, of course, they're in nanoliter volumes under oil, and the supersaturation is achieved upon mixing. So you really make the drop, put it under oil, and put it away to bake. Again, for those of you who are just joining this webinar, I just want to briefly describe the phase diagram. I was saying that when you take two parameters which are often varied in a crystallization experiment, and you get a two-dimensional phase diagram, and you see the lines which are saying A, B, C, and D represent the different methods of crystallization, showing that they take different routes to get to their destination. So each method needs to go through the nucleation zone and get to the metastable. They just do it via different ways. So, for example, if you look at B, what I was talking about, the vapor diffusion, it starts with undersaturated. The ingredients, both protein and precipitating agents, are enhanced during the trial, whereas batch, which is A, you just go direct into the supersaturated conditions, and eventually it gets down to the metastable just in a different route. Now here is a case study when we this was carboxypeptidase G2, and we did, initially it was vapor diffusion. Everybody did vapor diffusion. We got these crystals and they looked beautiful and everybody was very pleased until we put them under the microscope just to examine them, and the crystals dissolved under our very eyes. And we couldn't do anything, just couldn't get. You got the crystals, they were reproducible, but they were disappearing. And then we changed and put those the same trials, but under microbatch under oil, and the crystals were stable. The crystals could come out, they diffracted, and this really saved the day. And then eventually, because of cryoprotection and so, people wanted to do it with glycerol and decided to try again the vapor diffusion with adding glycerol, and that was okay. So it worked. So we went from vapor diffusion to microbatch, and then back to vapor diffusion. But you could get it if you didn't necessarily need the cryo. You could just take them from these beautiful crystals which grew in the microbatch. So that's one scenario where one switched, and that was important. And then was another, a snake toxin, and by that time we had the robot, and it was much easier to do the screening in microbatch. At the time, this was again before the days where there was all this nano screening in vapor diffusion. The microbatch was one of the first that you could do those very small quantities, and it was easy to screen. And we got this, as you see, sort of, you could see that it's crystalline, but couldn't get any better than that. So didn't know what to do, and one started adding additives to it. Still didn't work. And then we thought, let's now try to convert it to vapor diffusion and put in this additive screen. And one of the additives that worked was dioxane. Now, of course, in the oil, the dioxane didn't work because this is a small organic molecule, and it ran away into the oil. So it wasn't, it couldn't be crystallized in oil, and you had to go back to vapor diffusion. But one had here the best of both worlds, because one could screen using the microbatch, which was very small quantities, get a hit, and then take it to vapor diffusion and optimize it there. And this is an interesting story of, this was a lobster beta-crystallizing, where people tried to crystallize it for 20 years. I'm not exaggerating, using every method, vapor diffusion, liquid diffusion. It went into outer space to be crystallized, couldn't get. And Peter Zagalski, that was his project, and he made the protein. He heard then that there is some crazy woman at Imperial doing something with oil. And he came to me and he said, look, Naomi, I don't know, I've heard that you do. I'm so desperate. Can you try this with your oil? I said, I'll try anything. So I try and I put it in and I see that nothing. 2 months, 3 months, nothing is happening. The drops are clear. This is a blue protein. The drops are lovely blue, sea blue, but no crystal. And I said to him, Peter, look, I think, no, this is not working. And then, I don't know, 4 months later, I came to clear out the cupboards and looking at the crystals, and I see this beautiful crystal there, which diffracted, and we got the structure of it. And this could only be done using microbatch, because you see the paraffin oil is doesn't allow any evaporation through it. But of course, there's no such thing as zero evaporation. And even 14 parts per million over enough time will give you something. And this here, it needed 4 months, and it needed its slow, very, very slow evaporation, and that's what did it. And we couldn't hurry it up. And taking to vapor diffusion, even once we had the crystal, so didn't work, only in microbatch, and took its time. But it was really worth waiting for after all these years. So that is one of the other interesting stories there. So this is just the table, just shows about protein crystallized in vapor diffusion and microbatch, showing the success of each. Now, I would say 80% of cases, crystals will grow in both. There are some where you couldn't, like I showed this crystallizing, which needed a long time. And some others which only will grow in one and not the other, and we're not always sure about. Well, in the snake toxin we knew because it was to do with the additive. Then there was a protein called AMI-C, which also could only crystallize in microbatch. I don't know why. And eventually we see more and more that there are crystals that can only crystallize in microbatch and not in vapor diffusion. But then, of course, there's also the other way. So the conversion between the methods is easy. You use relatively the same conditions. So if you get a hit of some crystals in vapor diffusion, you take the microbatch plus minus the conditions and see. You set up a few drops. And maybe microbatch, usually it's a bit lower because the microbatch already from the beginning has got the conditions which vapor diffusion would reach after a long time. But in general, I wouldn't worry too much. If there's conditions, I just set up similar conditions, maybe, as I say, a bit lower, a bit higher, in the opposite method, and see what happens. So we did microbatch for a long time, and then we saw that the oils, it's not only microbatch, but oils themselves can contribute a lot to crystallization experiments, whether it is screening, optimization, and also for nucleation, control of nucleation and equilibration. And one of the things which, like I was saying, the paraffin oil does not allow evaporation through it, and it's good when you want to keep the situation steady, you know where you are. Say, for example, you want to dilute an experiment, then in microbatch it's easy. You know that the conditions are so, and if you dilute, they will, for example, what I was talking about, backing off from conditions. If you dilute, you know exactly how much and what's happening. But for screening, Alan Darcy, who you might have heard of, he said that for screening, he thinks that the paraffin oil is sitting there and not giving him crystals. He said, why not use an oil which does allow evaporation. And he really introduced the use of silicon oil or mixtures of paraffin and silicon oil. It's called ELS oil. Hampton Research sells it. Actually, everybody does now, but initially they named it ELS oil. And there, what you do, you screen, and especially when you don't get crystals, or when we were talking about clear drops, you can put them under oil, and this allows concentrations of the trials, but eventually the drops will dry out. So you have to be there very carefully to watch when this happens, because otherwise they can dry. And my experience, that although as many things, the theory says that it will work or it won't work. So really paraffin seems that it won't work, but over time it does. And it's safer from the point of view. If I have to choose, I even screen with paraffin oil, because over time you get crystals. Here there is this problem of drying out, but you can overcome it by topping up the oil. So you look at the crystals, you get the hits, and once you get them before they dry out and go just precipitate or completely dry, you can top up the oil, either with the paraffin or silicon paraffin. So you can do, but that means actively following the trials almost every day. Otherwise, you can lose a lot of drops to drying out. Whereas with the paraffin, this doesn't happen. So again, some people swear by the mixture of oils. Some people, like me, actually prefer the paraffin. Now, one question that many people ask is, can the oil techniques be used to crystallize membrane protein? And the surprising answer is that you can. And this is really counterintuitive, because you'd really think that these are lipophilic and that they would go into the oil. And this, interestingly, doesn't happen. And again, these were the very first membrane protein crystals in oil was of CP43 from the photosystem 2. That was before photosystem 2 was actually crystallized. And again, somebody came to me and he says, oh, I want to do this. And so I said, well, I'll try microbatch. So they said, no, you'll be wasting your time. These are lipophilic and they won't work. I said, no, I'm an experimentalist. I'm willing to risk wasting my time. Let's see what happens. And I set up for screening with the robotics. And lo and behold, you get these little thin needles on your left, and after fine tuning you get proper crystals, and this is all under oil. And in the meanwhile, many people have got membrane proteins under oil, and here is a list of only some of them. And what is interesting, that it is often, not often, but that there are cases, and quite a few cases, where membrane proteins will only crystallize in microbatch under oil and not via other methods. And this could be, we were thinking, it was with Ben Henkamer that we did the very first membrane protein under oil, that was back in '92, and came up with a theory that it could be that the oil is needed to mop up the excess detergent. So, of course, for membrane protein, you need to solubilize them. And then if the oil is sort of gradually absorbing the excess detergent, it allows it to gently come out of solution. Now, we don't know whether that is true or not, and people have tried to check it to see whether stuff is coming out. The jury is still out on it. Why? But the bottom line is that if you have a membrane protein and you've got a problem and it doesn't crystallize, it's absolutely worth to try with microbatch. This has happened now time and time again, that people have tried and for years didn't work, and microbatch gave them crystals and diffracting crystals. And so it's very interesting and a marvelous surprise almost, but it works. And that also, that was still, somebody did a PhD and tried to see, is it a detergent? Does it matter which detergent? Look, a variety of detergents, and they're all working within the oil and the microbatch. Now here is a bit of a fun experiment with oils, because I was saying that about the nucleation, that one wants to create environments with a bit less nucleation. And of course we know that chemists, for example, they make a scratch in a dish in order for it to act as a nucleant. But often you don't want too much of it. And here you see on your left two little vials, one with a microbatch experiment with a drop just under oil, and the one on your right drop between two oils of different densities. One is high and one is low, and the drop sits between the two. And because it's not touching the container wall, this again we tried with the carboxylic peptidase G2. You see the picture on your left, that comes from just normal microbatch, and the one on the right is with the limited nucleation environment, so we get 2 or 3 crystals which are larger. Now doing this, this is the idea of it, sort of between two oils. This is fiddly. I wouldn't advise anybody to start fiddling between two oils, but you can do it now in high throughput. You can just, those plates that we would put under the robot to do just normal microbatch. If you take a layer of Vaseline and on top of it paraffin oil and dispense your drops, you get this containerless crystallization, and just done by the robot. And but of course, again, this is not for screening. This is for optimization. For screening, you want to get a lot. But when you want to get them down to a few, then this is, again, an easy method to do it, and even by hand. Microbatch is very, very easy to, it takes minutes, and anybody who's been to any workshop has seen it. And in every, I think in most places, there are people who know how to do it. It's worth asking. It's really a question of minutes. Sometimes it's quicker to do a plate manually even than by the robotics. Another thing which oils are helping in is the making crystallization in gels into high throughput mode. Crystallization in gels also has become, it took a while, people didn't want to use because it was fiddly. Now it's getting more in vogue to use gels. But to my knowledge, the only way to use it in high throughput and in robotics is by dispensing the drops already with gels, dispensing the gel and the drop simultaneously under oil, and you get better results due to the oil, and can do it easily. Again, either high throughput or even manually under the oil is much quicker than to do it in capillaries and that sort of. Now, big question that comes always whenever I speak of microbatch is people say, how do we harvest? How do we get the crystals out of there? They're sitting in the oil, can we get them? So it's really quite an easy procedure. You just add harvest solution or cryoprotectant solution into the well containing the crystals. So the crystals are sitting there under oil in those wells which I've shown. You wait a while, probably usually enough 5 to 10 minutes, but say up to 15 to make sure that the crystals are equilibrated and they're not cracking. You then withdraw the enlarged drop, because yes, you've got your drop, you've added say 5-10 microliter to that 1 microliter drop of the either cryo or the harvest solution. You withdraw this whole enlarged drop from the under the oil by just using 10 milliliter pipette, which has its tip cut off with the scalpel in order to widen the bore. So if you can imagine those yellow tips or white tips, just cut the bore, the bottom of it off, and that gives you a larger bore. And you can just suck up the whole thing. If the crystals stick to the vessel, you can loosen them gently inside the drop using micro tool or strips of filter paper. And then you just transfer the drop into a depression well containing more harvest solution, and you handle them as if you would from a standard diffusion trial. So really the trick is just to, as I say, make the solution a bit more and then take it out. Sometimes you can even just go in with a loop and fish it out of the oil. So either way does work. Yes, of course, you need maybe a bit more deftness than if it's in a hanging drop and you can get it out. But when you've got crystals, believe you me, it's worth the effort to get them out. That it's not really difficult. It sounds more difficult than it is. So we see that the contribution to oil can be in many ways. It enhances accuracy. It's clean because it's under the oil and it's protected there. It's more reproducible because it's, as I say, the cleanliness, the protection of it is good. You can take crystals even to synchrotron. You don't need to harvest them immediately. You just you can take the plate as it is with the oil. It's no problem. And nowadays we're getting more and more possibilities to X-ray even within the plates, and so you sometimes probably don't even need to harvest them. And the crystals are certainly more stable, that we've seen again time and time again. So like I was saying, some crystals will only grow in oil, and they can grow under the controlled conditions, as I was showing, by choosing the oil which covers the trials, by varying the thickness of the oil layer covering the trials, as we were saying with the ELS oil and topping up the oil, and by applying the containerless setup. There is one limitation of microbatch, and that is that you cannot use small volatile organic compounds. As I was showing with the snake toxin, you can't use phenol, missing the thymol, or dioxane. But interestingly, the bigger ones, MPD you can use, glycerol you can use, all the pegs you can use. So it's really not a problem. It's how often do you need thymol or dioxane, but when you need these, microbatch will not work. Isopropanol you can crystallize as well. Everything actually, it's these very small organics that you can't. And now last, to finish with one of my favorite methods, which alters the kinetics by inserting an oil barrier into hanging drops. And the idea of that is when crystals form too quickly, then often they form very small and they're not good enough. And since already we're so much into the oil, and some people said, oh, we don't want microbatch, can't you do something in oil with vapor diffusion? We love vapor diffusion. I said, okay, I'll try to find something. And came up with the idea to put a layer of oil in vapor diffusion experiments in order to slow down the crystallization process. So if you take a standard trial, which you see on the left, you see those two Limbro or whatever crystallization vessels, you take a standard trial as you would. So you take the conditions which give you the small crystals. And then you all you do is put a layer of mixture of paraffin and silicon oil, about, if it is 1 mil, or 700 microliter of reservoir solution, you put half a milliliter of a mixture of paraffin and silicon oil, and then put the cover slip on with a drop and let that let it cook. And it takes about, instead of 24 hours, which you get the bad crystals, it may take about 10 days to 2 weeks. But if you look on your left at the crystal pictures, the difference is really enormous. This can make a difference between getting small crystals which really don't diffract or don't diffract well enough, to large crystals which are really diffract to fantastic resolution. If you look at this lobster protein, this is another part, not the beta, which I showed with microbatch. You see on your left the control, you get sort of some diffraction. The one with the oil barrier, it's slow, but gives it time. It diffracts to 1.3 angstrom, which is really gave the structure. And then the top one, again, you see these many small crystals and then fewer. And sometimes they're not much bigger. They don't always have to come to this enormous size. Sometimes 10 micrometer in the thickness who can make all the difference. And again, this has happened. Many people have used it successfully. Again, so easy. You don't have to do anything. All you have to do is take a layer of oil and put on top of your reservoir before you put the cover slip back on. Now, you could also do it in different ratios, because sometimes you see that the half and half works, half paraffin, half silicone works well in most cases, but sometimes you want to slow it down even further, and then you can take 70% paraffin and 30% silicone. Or you want it quicker, you do it the other way around. You take 60% silicone and 40% paraffin. So that is easy too. Or you can change it doesn't have to be half a mil of the oil layer, it has to be maybe 300 microliter. Now this, of course, you can only do manually, but this is when this is optimization, when you've got the conditions, and you can, then you do. It doesn't matter to do manually. Now, there is a limitation, which I still don't understand why this happens, but this method doesn't work if the reservoir contains PEG or MPD above 15%. And that's very odd. I don't know why. With salts, it works completely all right. Even with PEG, MPD, isoprop, all these, if it's below 15%, you get the result. If it's above, you just don't get it. The crystals become worse, and I don't know. Years I've been trying to figure out why. I don't know the answer. So don't waste your time if your precipitant is above 15% of those. Now, one thing that I cannot give a crystallization presentation without mentioning, the crystallization in outer space. Now, of course, this is a very controversial subject, and people have been debating about it for a long time. But for me, I was lucky. I had possibilities. I mean, if they would have given me a postdoc in my lab, instead of this, of course, I would have taken. But since I had the chance, and I didn't have the choice, but had the chance, I have been on, not have been myself, but have sent experiments with NASA, with photon satellites. NASA was manned rockets, the Cosmos, which was the unmanned photon, and got very interesting results, because we could do systematic studies there. And here is just where I was in Moscow, and this went on a photon. And these crystals that you see on your right-hand side, that's reverse transcriptase. And there is me looking under the microscope. I was so happy. And you get these diamond crystals, and they don't deflect a single spot. So there you go. But we did get quite a lot of systematic studies showing interferometry and things, which gave some knowledge onto the systematics and how things work, which one could do in space and not so easily do on Earth. So, in summary, my bottom line message is keep an open mind, use a variety of techniques rather than just one or two that you're used to, and I think in many cases it will bring joy. Thank you.